In this video, we're going to look at reading and writing inequalities for linear programming in decision maths. What I've done is written a question here. It says, Steve makes stuffed dogs and stuffed cats. Let X be the number of dogs produced, let Y be the number of cats produced. We're asked to write the following as inequalities or constraints in linear programming using integer coefficients in their simplest terms. So we've got 8 different questions. The idea is to look at these as many different ways as it takes for people to understand them. Some people just look at them and write them out. Some need to take alternative methods to get their head around it, which is perfectly fine. Let's just start off with some basic notation. If we have now X and then the inequality sign greater than Y, this means that X must be bigger than Y. This is a strict inequality. So it can't be equal to, it must be bigger. If we have now X less than Y, we can say now that Y is greater than X or X is less than Y. If we have X equal to or greater than Y, we use this particular symbol. So X could be Y. If we have now X equal to or less than Y, again, it's an inclusive inequality, and we could say that X is equal to or less than Y, or Y is equal to or greater than X. If we were doing a linear programming problem, if it's a strict inequality, we'd have a broken line, so it couldn't include the value. And if we had an inclusive inequality, it could include that value. And for that, we would draw a solid line. So we could pick values along this line, but we couldn't pick values along these lines. Okay, let's start off. So the first one, the number of cats produced must be at least half the number of dogs produced. I'm going to write this out, and to begin with, it's going to seem quite counterintuitive. What we're going to have is 2y must be equal to or greater than x. This is the inequality that represents this statement. Lots of students think that we should have 1/2 y is equal to or greater than x. If we think about this now, we need 2 lots of the y to make 1x. A few different ways you could think about this. Now, if I said that 2y was equal to x, and I said now that y was equal to 4, then 2 times by 4, that would give us now that x was equal to 8. So we can see that this now statement would be correct, but we're getting double the amount of dogs, x's, as we are cats, y's. So we can say now here that 2 lots of the y value must be equal to or greater than the x. Another way of thinking about this, rightly or wrongly, is to draw a straight line. Now, I like to think about this as y is equal to 1/2 x. So if we drew this line, this is a straight line through the origin gradient of 1/2. So let's go ahead and do that. So what we've got then is something that looks like this. So this is the line 1/2 x. So we've got this point just here, and this is going to be x is 2 and y is going to be 1. We've got this point just here, we've got 4, 2. We've got this point which is going to be 6, 3. So if we look at this, remembering that this is the y-axis, so we've got y and we've got x just here, we can see now that the number of dogs, x, is going to be 2, and the number of cats, y, is going to be 1. So we've got now here 4 dogs, 2 cats, 6 dogs, 3 cats, and so on and so forth. If we wanted to actually graph this and shade out the region we didn't want, we could do that. Now we've got 2y is equal to or greater than x. So I know I'd use a solid line, and this is the line y is equal to 1/2 x, or if you like, 2y is equal to x. People like to think often with these lines as, well, it's pointing above it, so we shade above it. I just like to take a point and confirm that that point is true. So if I just pick this point just here, this point is going to be the point 0, 3. I say to myself at this stage, is 2 lots of the y coordinate bigger than the x coordinate? Quite clearly it is. So this is the region that we'd want, and we'd shade out the region that we didn't want. So what I've done now is defined what we call in linear programming my feasible region R to be above the line. So if you wanted to think about the way in which the the arrow or the inequality sign is pointing, you can do, or you can simply test a point. So this would be our feasible region R, and all values below the line would be excluded. You could of course write this as y is equal to or greater than 1/2 x. We're asked for integer coefficients, hence why I've written it like so. An equally valid statement for the first one is that y would be equal to or greater than 1/2 x. So if you want a nice easy way of remembering it, we simply multiply now the variable we're talking about by the reciprocal. 2 is the reciprocal of 1/2, or if you like, 1/2 is the reciprocal of 2. Okay, let's look at the next one. The total number of dogs and cats produced must be no more than 300. Now, x is the number of dogs produced, y is the number of cats produced, so the total number will be x plus y. Now here, this says that it must be no more than 300. So this is an inclusive inequality, and we can say now that 300 must be equal to or greater than x plus y. This is the total number of stuffed animals produced, and now we have that it must be equal to or less than 300. Again, if we wanted to graph this, we could go ahead and do this. So if I pick this point, let's say that this is going to be 100, 200, 300, 100, 200 and 300. The way I like to do this, and I'm just going to write that this is 300 here and this is 300 here. So this is 300 naught and this is naught 300. I like to think about when I'm graphing this to set one of these equal to 0 and solve for the other one, and then set the other one equal to 0 and solve for the other one, if that makes sense. So if we said now, if x is naught, y is going to be 300. If y is naught, x is 300. So all I'm going to do is pick these points on here, and we're going to have naught 300 and 300 naught. When you're doing linear programming problems, make sure you label up the line. Y, and we can say this is x plus y is equal to 300. So that gives us now this line. If we wanted to actually show this inequality, we could test a point. I always like to test the origin, in this case 0, 0. So I say to myself now, is 0 plus 0 300 or less? Quite clearly it is, so we want now this region right here. So we shade out the excluded region, and this now is the excluded region above the line. Again, entirely up to you on how you want to view this, but all of these values wouldn't satisfy now the linear programming problem we were looking at. We would call this the feasible region R. So I just write on the R. So we can see this point 100, 100 is in it. We can see this point 100, 200 is in it, and I can find all manner of points in here. When we come on to linear programming and looking at the optimum solution, we're going to be able to take any valid solution in this feasible region, but we will look at the vertices to find the best one. So x plus y is at most 300. Okay, let's now look at the next one. The number of dogs produced must be less than 4 times the number of cats produced. We can write this now as 1 over 4x must be less and strictly less than y. Okay, if we want to write this with an integer coefficient, we can say that x must be less than 4y. Just think about this again. If you wanted, and these are two equal statements, the only reason I'm writing it like so is that we want an integer coefficient. If I said now that x was equal to 4y, or 1/4, if we write 1/4 x is equal to y, and x was equal to 40, then y would be equal to 10. Now let's just look at this. The number of dogs produced must be less than 4 times the number of cats produced. We can see now that this is 4 times the value, and we simply introduce the inequality. So that's how I'd write it if we weren't asked for an integer coefficient. This is with the integer here being 4. So this is what we end up with. Now again, I've seen that it's 4 lots of the dogs, therefore I've simply, if you want to remember a different way, is that I've written the reciprocal. 4 over 1 gives us a reciprocal of 1 over 4. So that's what we have. Again, with this one, we could draw a straight line from the origin and look at points if you wanted. I like to get a sense of what's happening by substituting values into an equation and then considering it now the inequality. You certainly don't have to, but that is an option for you. Okay, let's now look at question 4. The number of dogs produced must be at least 1/4 of the total number of items produced. Okay, so I can write this two different ways. I can write now that 4x must be equal to or greater than x plus y. Remember, x plus y is going to be the total number produced, or I could write it the other way round and write it as 1/4 of the quantity x plus y. So that's another way to think about this. So the number of dogs produced must be at least 1/4 of the total number of items produced. This is the total number of items produced, so I've written the reciprocal. Now let's look at this and look at it fairly straightforward from here. We need to give this in its simplest form. At the moment it isn't. What I can do, and I'll take this one for example now, is simply subtract x from both sides of the inequality. So we can say that 3x will be equal to or greater than y. If I'd taken this one, we would have multiplied both sides by 4, which would give me 4x is equal to or greater than x plus y, and then we would have substituted. Substituted x from both sides. So 3x will be equal to or greater than y. So I've just written that now as the statement. Okay, let's look at question number 5. The total number of cats and dogs produced must be more than 100, but no more than 400. So if we do that, we're going to have 100, and we've got more than. This is going to be a strict inequality, and then we're going to have x plus y. X plus y is the total number of the dogs and cats produced, and this now has to be no more than 400, and that's how we could write it. I could split this into two inequalities. It's especially easier, in my opinion, to graph this as two inequalities. X plus y is strictly greater than 100, and then we can have x plus y is equal to or less than 400. So if we wanted to graph this, x plus y now is going to be greater than 100. So if x was 0, y would be 100. If y was 0, x would be 100. So on the grid here, I'm just going to go ahead and do these. So let's go on and I'll do these. This is 100. I'm just going to write them as 1, 2, 3, 4, and so on and so forth. So we've got 500 and so on. So these are in hundreds. 100, 200, 300, 400, and then we can have 500. Again, I could probably make better use of my scale. So let's look at this first one. So what I'm going to now draw is the line on here that x plus y is equal to 100. So I know that I'm going to have 0, 100 and 100, 0. This is a strict inequality, so I'm going to have a broken line. In fact, let's make that slightly clearer now, and we'll go with this one. Let's try this one. That one should look a bit, there we go. So I've got this point, 0, 100, 100, 0. I'm just going to write on here now that x plus y, so just labelling this up. We need to label these as when we come on to linear programming problems, we're going to have to look sometimes at the intersection of two lines. Now, if you don't have the equation on, it becomes quite a hassle if you've got 4 or 5 lines on there. Now, we need this to be greater than 100. I always like to test the origin 0, 0. Is 0 plus 0 greater than 100? The answer is no, so we would shade out below the line. So the feasible region is all values strictly above the line. It's not going to include the line as this is a strict inequality. If I did this one, I could set x to 0, that would give me y is equal to 100. Then I could set 400, and then y to 0, x would be 400. So that would look something like that. So what we've got then is the line. Remember, with all of these linear programming problems, the non-negativity comes in, hence why I've got now just the first quadrant. So I'm just going to label this up. We're going to have x plus y is equal to 400. So I've got 400, 0, 0, 400. Now we need this to be equal to or less than, so I'm going to now shade above the line. So you might have taken this on as a single double inequality, if that makes sense, or you might have split it up. So now we can see all of the values above the line is included, all of the values above the line are now excluded. Therefore, the feasible region R is slimmed down to these values here. So if you wanted to pick one, we would go ahead and, for example, 100, 200 works. We could pick 200, 100. We could pick 0, 400, 400, 0. We couldn't pick anything in here and anything up here. Often in the textbooks, it's only shaded out so far. We know this is not the feasible region. Again, when we're looking at a linear programming problem, we might want to minimize the cost, or we might want to maximize the space of a profit. Generally speaking, now when we're looking at those problems, when we minimize, it's one of the first vertices that it's the first vertex we go through, and then when we maximize, it's the last one as we're leaving the feasible region. And again, we will look at that in later videos. Okay, so that one's done. Let's now look at another one. The number of cats produced must be between 10% and 40% of the total production. So we know the number of cats is Y, and what we're going to have then is the following. So it must be between, so it can include. I'm going to write this as 1/10 of the total production. The total production is X plus Y, and then it must now be no more than 40%, which I'm going to write as 4/10, X plus Y. You can, of course, write 10/100. You could write 2/5. What I'm going to do at this stage is multiply through this inequality by 10. That will give me X plus Y. Then we're going to have 10Y, and then we're going to have 4 lots of X plus Y. I'm going to split this into two inequalities. The first one is just here. X plus Y is equal to or less than 10Y. So we can say that X would be equal to or less than 9Y. That now is one constraint. If we look at this one, I could divide both sides by 2. I'm not going to bother. I'm just going to write that 10Y is equal to or less than 4x plus 4y. So we can see from here now that 6y is equal to or less than 4x. Dividing both sides by the 4, we're going to have 3/2 as a simplified fraction is less than or equal to x. We're asked for it in this particular form, but we could write it like so. So these are two constraints that have arisen now from the number of cats being produced between 10 and 40% of the total production. So we've ended up with these two straightforward inequalities with integer coefficients. I'd be potentially more inclined. In fact, we can simplify that one, can't we? Let's just write that as 3y is equal to or less than 2x. So that's 1, and then x is going to be equal to or less than 9y. So they're the two that should have arisen from that in their simplest form. And again, with this, we could draw two lines, and then we could look at a feasible region that satisfied both of these inequalities. So two straightforward straight lines, and then just considering which side of the line we shade. Okay, let's go ahead now. The next one we've got here, number 7. For every 5 cats produced, there can be no less than 6 dogs produced. Okay, what we're going to have here is 6y, and then we will have is equal to or less than 5x. Let's think about this logically. For every 5 cats produced, there can be no less than 6 dogs produced. This is the inequality that we wanted. So if we look at this now, if we had 6y is equal to 5x, and we said now, for example, let's just say y is equal to 5, okay? If y is equal to 5, we've got now 30, and that's going to give us now 5x, so we can see that x would be equal to 6. So if you're thinking, why have I put it that way round? This goes back to where we were before. So x would be equal to 6, and we can see for every 5 cats now we've got 6 dogs. It's just simply writing it essentially backwards. Again, integer coefficients there. If you were unsure, you could go ahead and just sub in values. We could, or we could write now that y is equal to 5, 6 is x, and you could go ahead and draw now a graph and just check that that's going to give you what you want. Some people see it visually. I'm entirely, as I say, I really don't mind how you want to see this. So if we wanted to graph it, let's put 60 there. Let's go ahead and put now 50 there. What we'd have now, let's go through this point here. If you wanted to graph this, entirely up to you. So this is what we're going to have, and we have this point now on the line, and this is the line y is equal to 5, 6x. So y is equal to 5 over 6x. This is going to be the point now 60. Let's write in 60, comma 50. So we'd have now 60 dogs and 50 cats. Again, when you're deciding which side of the line to shade, this should be relatively straightforward. We're going to want to keep this region right here, so we would shade out now the other side of the line. So that can go, now that the line will be included, and we would say now that this is the feasible region R. So we'd have this region R. Now just think about this, just pick a point, pick any of these points. This one's going to be 30, 0. Does this satisfy the inequality? Is 30 lots of 30 lots of 5 lots of 30 bigger than 6 lots of 0? Quite clearly it is. This is a region we want. We get rid of that one. Okay, let's look at question number 8. The number of cats produced must exceed 1/2 of the total production. So all I'm going to do, it must exceed. That means it's got to be bigger. So we can say now that 2y must be greater than x plus y. We could have written this now as y must be now greater than 1/2 x plus y. I want integer coefficients, so this one is going to simplify really quite nicely to y must be greater than x. So hopefully you can see by now that algebraically we're simply writing the opposite statement. We need 2 lots of y to be greater now than x plus y. Right, let's move on. Same question. Steve makes stuffed dogs and stuffed cats. Let x be the number of dogs produced. Let y be the number of cats produced. We're asked to explain what the following inequalities or constraints mean in the context of the question. Okay, these are typical exam style questions that often trip people up. We're going to look at this one first. 4x is less and strictly less than y. X is the number of dogs, y is the number of cats. I'm going to read out possible statements for these, and I can think of lots of different ones. If you pick a certain, your preferred statement, stick with those as you go. So the first statement that I'm going to make is that the number of cats must be more than 4 times the number of dogs. So I'm looking at this one right here. And just think about this now. 4x is strictly less than y. So the number of cats must be 4 times the number of dogs. Again, if you put a number in here, let's say that x was equal to 1, and we had now that 4x was equal to y, then this would give us that y was equal to 4. And you can see right now that we have the inequality correct. Let's read another statement that we could say satisfies this now, or essentially explains this in the context of the question. We can't just say now that 4x is less than y. The context of the question here, what we're looking at is relative to now the number of dogs and the number of cats produced. So here's the next statement. The number of dogs must be less than 1/4 of the number of cats. Now, if we think about this, it's essentially reading the statement I just read out, but backwards. The number of dogs must be less than 1/4 of the number of cats. So that's another way that you could say that. An alternative, for every 4 cats, there must be less than 1 dog. For every 4 cats, there must be less than 1 dog. Another thing that you could say, and this is slightly less intuitive and potentially not really in a mark scheme, we could say the number of cats must be more than 4/5 of the number of total animals produced. So let's read that again. The number of cats must be more than 4/5 of the number of dogs and cats produced, or the number of animals. Again, we can see this here. If we think 1 and 4, it's going to be 4/5. Alternatively, you could flip that round. You could say the number of dogs produced must be less than 1/5 of the total number of items produced. So different ways to read that. So I've given about 4 or 5 different ways. So the first one, the number of cats must be more than 4 times the number of dogs. The number of dogs must be less than 1/4 of the number of cats. For every 4 cats, there must be less than 1 dog. The number of cats must be more than 4/5 of the number of the total items produced, or the number of dogs produced must be less than 1/5 of the total number of cats and dogs together. So different ways to look at that particular inequality in context of the question. You can't just say that, for example, 4x is less than y. You need to make some reference to the dogs and cats. Okay, now x plus y is greater than 100. We would say now that the total number of animals produced is more than 100. That's nice and straightforward. So the number of dogs and the number of cats together is more than 100. Right, let's look at this one here. 3y is going to be equal to or less than 5x. This is very similar to the one just here. The difference is now we had 1y and 4x. So we can read this one slightly differently. What I'm going to say, again, a few different approaches for this one. For every 5 cats produced, there must be at least 3 dogs. For every 5 cats that are produced, there must be at least 3 dogs. We could say from this now the opposite to that statement if we really wanted. An alternative statement we could make is that the number of dogs produced must be at least 3/5 of the number of cats produced. If you think about this, if we rewrote this now without the integer coefficients, we could say now that y is equal to or less than 5/3 x. And remember, from our work before, we saw now that it's simply the reciprocal of this. So let's read that statement again. The number of dogs produced must be at least 3/5 of the number of cats produced. Of course, we could switch this over and we could write this now as 3/5 y is equal to or less than x. And we could say now that the number of cats here, we could say that 5/3, or rewording it slightly, the number of cats must be at most 5/3 of the number of dogs produced. That's a bit of a mouthful, but it means exactly the same. So if you see now it in this form, you can do. I prefer to think about it now, for every 5 cats, there must be at least 3 dogs. So that's one way of doing it. Again, looking back at the one we did with the fractions, we could say the number of cats produced can be no more than 5/8 of the total number of items produced, or the number of dogs produced must be at least 3/8 of the total number of items produced. So lots of different ways that you could say it. Pick one. These ones are the harder ones to do. But it's entirely up to you. Think about it if you want to sub numbers in, if you want to graph it, it's entirely up to you. Okay, let's finish with this one. We've got now x minus y is equal to or greater than 4, yet in turn equal to or less than 6. Now, the difference between the number of cats and dogs produced is going to be between 4 and 6. We've got a difference this time, so slightly different if you excuse the pun. So a difference. The difference between the number of dogs and cats produced is between 4 and 6. That's how I would read that one. You could read it many different ways. That would be my first choice. If you wanted to split the inequality up, you could do. What I'm going to do is write two different inequalities. We could say that y plus 4 is going to be equal to or less than x. And we could say now that x will be less than or equal to y plus 6. So if you want to read this in terms of the number of dogs relative to the number of cats, and the number of dogs relative to the number of cats, you can do. So with this one, you could say now the number of dogs must be at least 4 more than the number of cats, yet in turn it can't be more than 6 more than the number, let's get this right, the number of dogs can't be any more than 6 more than the number of cats. So after half an hour you can see that I'm even struggling to read these, but just think to yourself, how could they be written? How could I think on working out whether my inequality is correct? So hopefully that's made some sense to you and helped you out on the problem. As stated at the start of the video, each method isn't for everybody. You might think that some of it is mathematically a little dodgy. That's entirely up to you on how you want to do it, but think of a method that you like, and also think of a method in which you could use to write these in the context, in context.